Speak up yourselves. Yeah, that's what helps. Okay, so what we were doing last time, so we can mention now, so last time we were looking at the distinction between by name languages, that are variables, range over computations that are possible to define. And we looked at by value languages, where value variables range over values, things that are already computed, that have been finished computing. And the fact is that these things come apart. That these come apart in the presence of divergence. Okay, that was the thing I started out by talking about. I'm sorry, I think I might be writing too small. So we were looking at that distinction, and in particular, that was a way of kind of relating two different approaches to the semantics of variables in programming languages, and I was trying to illustrate the relation between them. And the thing I was pointing out is that by using this computation modality, by that notion, enables, I don't know what to say here, a kind of the combining or using by name methods within a by value setting. Maybe that's the best way to say it. By name methods, if you want to use them, sometimes they're useful within a by value setting. And the converse isn't possible because there's no control over the order of evaluation. And the critical thing here is that we have an explicit control, the elimination form for the computation modality to the sequencing. So we control the sequencing of evaluation. So we control which order things are done. And then we can relax them by saying, well, if I don't want this to be evaluated now, I'll label it as having a different type, and it will be by virtue of being a value of that type, let's say an unevaluated computation. And so then we can recover, for example, by name functions, for example, we could talk about a tau computation to a tau prime, let's say, computation. This being the partiality in producing a computation as a result, and this is taking unevaluated computation as argument. So that would be an example. So we get that. So it controls sequencing. And then what's nice about that is that en passant, it provides a natural way to account for exceptions. Not counterexamples, but program exceptions. And so what we do is we have a way of accounting for that. It's very natural because you just say, well, there's two forms of termination, so to speak. The sequencing sequences the termination behavior, which was motivated by the divergence. And then you say, well, there's another way to sort of explicitly decline to terminate in the ordinary sense. So we raise an exception. And so en passant, we can just generalize this idea slightly to allow for the possibility of raising and handling exceptions. So that I found to be a very elegant thing, and it falls out very nicely, in this kind of perspective. If you're trying to use exceptions in a situation where you have no control over the evaluation order, it's at the very least painful. It's well defined. I mean, you can write down a semantics for it, but good luck knowing what you're doing. Okay, it's a similar issue as to what Jan presumably is talking about. You need to have a by value interpretation if you wish to reason about the complexity behavior of some program. If you do it by name, well, good luck with that. Okay, you're not going to be able to do it. Okay, it's very, very difficult to do. So we gave you so this is like the fundamental thing that I was looking at last time. And then I said, but isn't that actually terrible? Oh, yes, please.
Could you write larger, like 3 times as large?
Unfortunately, I have to walk over to you before I can hear you.
Could you write larger?
Oh, I'll try, yes. Yes, you can just do something like this to tell me to enlarge my writing. Okay. Okay, I'll do my best. Okay, so I'll work up my arm. Okay. So then the natural thing to think of is, okay, well, it's well and good to do this sequencing. As a matter of fact, if you think about ML, there's an order of evaluation of the constituent expressions, let's say, of an application. And curiously, whether you know it or not, OCaml does it backward from standard ML. I don't know. It doesn't matter, it's arbitrary, just do it, okay? But whatever you do it in a definite way. And then you say, oh my God, but isn't this feature a bug? Because now you're introducing sequencing, and what about parallelism? Oh, that's the thing that's extremely nice, because we can then relax or generalize the tau comp, which is one suspended computation, to any number of suspended computations. And in fact, I didn't speak about it, but I can also have a dynamically determined number of suspended computations by a sequence. And then I can then have the elim form, instead of being the elim form of bind for a single suspended computation, is a elim form for binding any number, either statically many or I'm just alluding to the fact dynamically many unevaluated computations. And I do sequence them, that's for sure. I sequence them, but there's no sequencing amongst them. There's only sequencing about, so if you're going to apply a function that has two arguments, there's no reason to evaluate the arguments, the function and the argument in any order. You can do those simultaneously, but of course you can't do the function call until you know what the function and the argument are. And so there is a sequencing, but you want to have the minimal sequencing which expresses a semantic dependency and then otherwise let everything fall where it may. And so that's what we're doing here. And then this gives rise to... And moreover, it shows you, when you think about it in this way, and I didn't develop all the fascinating ideas about parallelism. In fact, we devoted a week of the summer school last year to parallelism, so obviously I can't say very much interesting, but I can at least give you some sense here. And the point is that this line of development makes clear that it's entirely an issue by value. And why is that? Because you want to maintain the principle of work efficiency. And you can look that up. I'm afraid I can't take time now to explain that. It's possible. I'm not certain. Jan may have commented on this. Oh, he wasn't talking about parallelism probably, so never mind that. But the issue is work efficiency. You don't want to do work that you don't need to do. And so, for example, when I do a function application, I'm in a by-value setting. Variables range over values, so if I'm going to plug in an argument, do a beta reduction, I have to plug in a value. So I know for sure that I need the value of the function and the value of the argument. Okay, that's it. So I evaluate those simultaneously, and it's work efficient because I'm not wasting cycles evaluating something I don't need. Okay, that's the key idea of work efficiency. And that's a central notion in parallelism, and I'm going to have to leave it at that. Okay, but this can all be as a fascinating subject, and I can basically say it's a fascinating subject. Okay, so this gives rise to parallelism. So there's a nice line of development, at least that was my intention, is to bring out what I consider to be a nice line of development, which is to emphasize that the central issue is the meanings of variables, and they come apart from logic or whatever because of the possibility of, let's say, divergence or exceptions, as I emphasized here, different forms of termination or non-termination. And so you have to actually consider what do you mean? What are your variables range over? And so that's what we use as a motivation. And for that reason, I start using by name, but as I mentioned, we'll always say call by name and stuff. It's just baked in, okay? But my feeling is it's not really about calling by anything. That's not the issue, okay? It's a question of what are the maps, if you like to think in terms of categories or something. What category are we working in? Okay, so that's the idea. Okay, so that's a summary of a line of work that started in the late 80s to my awareness. Maybe that's just because that's kind of the span of my life in a way, but in any case, that's a kind of consolidation of a whole bunch of ideas that to my knowledge, started in the late 80s and have been developed up till now. So it's this storyline which is the reason why I feel that the by-value language is inherently more expressive, because I can relax the distinction by introducing a value of unevaluated computations. And then I don't get into all sorts of snafus about not having natural numbers, not having Booleans. Okay, I can't accept that, I'm sorry. It's just, you can decide I'm wrong, but that doesn't seem right to me. Okay, so that's the line of development that goes there. Okay, so good. So all right, so we'll keep that in mind. And the other thing I wanted to remark is you'll recall, and that's what's going to motivate what I'll do next, is that this notion of a fixed point or self-reference with which I modeled divergence here in the by name setting. I use that letter to stand for any expression. And this was done in a rather ad hoc way. And as a matter of fact, when I looked at self-referential computations, I also did that in a rather ad hoc way. And now what I want to do is get rid of that ad hoc way, because it's not an ad hoc notion at all. It actually arises out of more general typing considerations. So that's what I want to mention. Okay, so what's a nice thing is that I feel the experience has shown that, programming language features are manifestations of type structure. Now, it's a little bit elusive to make that principle really precise. It's a methodological thing. And one time, I made an aphorism out of this about computational Trinitarianism. Some people have heard of this. And it's just a way of sort of explaining, like, the methodology, the way we think about these things. So the consequence of that is that every concept, such as self-reference, ought to emerge as evidence of some kind of type structure that maybe we haven't quite brought out yet. So that's what I'll do next. Okay, so that's what I'm doing. So the subject I want to do this time is I want to look at a language called FPC. I think it was Gunter who called it FPC. It's sort of a permutation of PCF. That's the way I perceive it. And the idea is this is a language for recursive types. Okay, and by this I mean recursive types in a full generality. Okay, so fully general. In other words, there's no restrictions of any kind about positivity or anything of that nature. And so the origin of this is really Dana Scott's remarkable discovery of a kind of mathematical model, what's called a model of the lambda calculus, an interpretation of the lambda calculus in terms of a kind of topologically motivated view of function, an idea of continuous function. And it was one of the earliest things, if possibly the earliest thing, or one of the earliest things where people understood that there was some relationship between computability and continuity. And that continues to, like, bear fruit over decades. Yeah.
Would you state your aphorism, please?
Say that again?
Would you state your aphorism?
Oh, I'm a little bit reluctant, but the reason is I'm going to get stuck after I'm dead, okay? That's the problem. It was just a joke. But the joke was I called it Computational Trinitarianism. You can view computation from you get insights from different perspectives in type theory, categories or algebra basically, or logical systems, and there's an interplay along all three edges of this triangle. So I jokingly called it Computational Trinitarianism, and now I'm going to be stuck with that. Okay, so. But anyway, it does have some kind of instructive value to give people a sense of, like, what we're talking about here. Because I'm one of these people, rightly or wrongly, who has the idea that there's a right way to do things, and our job is to discover what the right thing is. And the programming language is not arbitrary constructions. I hate that. Okay. Now, as a matter of fact, okay, you can, again, you're free to disagree, but to me, most PL work is cults of personality. And that's not what I'm in this business for. That's not the idea. I'm trying to figure out what's true, okay? And so that's what I'm trying to explain. Okay, so there's a remarkable thing. So this Scott's model of lambda calculus. I'll start out with it in the by name setting because I want to address this, and then I want to separately address this. So where I'm heading is I'll first write down two sort of versions of FPC. I have to skate over some details, and I'll ask you to do the back reading, okay? But I'll give you some idea about it. And then I'll be able to explain these things in a systematic way, which is kind of nice. And then I will close, I think, today by talking about this idea of a universal domain, what Scott originally called a universal domain. But it's the idea of encoding all your, well, I'll get to it. It's the idea of unitype versus untyped languages. And in fact, that's Dana's terminology, unitype. He said, well, the so-called untyped lambda calculus should really be called the unityped lambda calculus. So, and I think that I agree with him, so that's good. Okay, so this FPC language is one codification of it. And what we now do is instead of taking fairly, again, ad hoc concepts like just the Booleans or the natural numbers, I don't know, it's a matter of judgment here about what we say, but let me just say that. I'm going to decompose things into more generic concepts of typing. So what we're going to have as types is we're going to have type 0, which is going to represent the empty type. we're going to have sums. I'll just do binary sum. This is convenient for like meta purposes, but in practice we sort of want, an n-ary sum. And in fact, a lot of times you want to give, label names to the components. Okay, I don't mind about that. That doesn't matter. Okay, so we can do that. I'll explain momentarily exactly what I mean there. But so I'm just trying to get that. It's a little bit Blackboard convenient to just do 0 and 2, and then we get any on. Okay, so that's what I want to do here. There's an analogous. So this is also called void. And probably by now, there's this horrible thing that in the seat of the pants programming world, that type is called void, and it's not void at all because it's not uninhabited. It has an inhabitant and only has one uninteresting inhabitant. But in all the commercial programming languages, it's always called void. There's incredible obsession with void. Okay, but anyway, it's wrong. It's actually unit. Okay, it has one element. So the thing that they call void in all sorts of commercial languages has nothing to do with the actual empty type. So, all right. It's just a curious thing. It's a confusion between not having a value versus having no interesting value. Those are different notions. Okay, that's all. All right. Okay, so one across. And then we will put in a function type, and I can put it in. If I'm going to do it here, I'm going to think of this as a partial function type, so perhaps I'll keep doing that. And what else do I want in here? I think the only other thing I want now is rect_t.type. And that's the critical thing because it binds a type variable in here. So I might as well start out with some examples. So I can define 2. So this will be the thing you can brag about learning at the summer school. 2, I'll have you know, is 1 plus 1. Okay, because it's 2 copies of the unit type. Because, I haven't really spelled that. I'm a little bit assuming we know what these things are. So let me mention what they are over here. So if we look at the statics, so I'll look at the binary case first of all. So if I look at the statics, if I have something of type tau1, then I can inject it, okay? And officially, I should really write down what all the types are. It's a little tedious if I want to make the syntax have certain properties, okay? And I'll say that that's a tau1, and that really should be, in1. Oh, it's terrible, isn't it? I mean, it's really terrible. So I'll often write that 1.e1, okay, which will be type tau1 plus tau2. And a similar thing is, if I take E2, then we just write it like this. You can look in the book for all the specifics. 2.E2 is going to be in, that should say tau2, tau1 plus tau2. So I get something that is discernibly either on the left side or the right side, and you can tell. And how do I know I can tell? Because I can case analyze. So the idea is I can do a case analysis. So if you give me something which is in the sum, then I can tell you, let me write it x1, e1, and x2, e2. Okay, and I'm going to say that's some type tau, provided assuming x1 is in tau1, we do the cases. Then we get tau, and x2 is in tau2, we do the cases, and we get tau. Okay, so that's the idea. And the dynamics of it is kind of what I just indicated. If I have 1.e here, and I have those arguments, which I won't write again, then the relevant transition would be in the by name setting that I'm doing e for x e1, and if I have 2.e, then it's e for x e2. Okay, that's the most I will say about this right now. So that's the notion. I guess I should say one other thing, which is what do we do about the empty type? Well, there's no intro rule for the empty type. That's the entire point of it being the empty type. So there's no intro rule for 0, but there is an elim rule. And I'm going to call it can't. And the idea will be, in terms of the statics. All right, let me write on a different board. This is another regret I have in the book. Okay, if I have 0, I'll call it can't e, and that will have any type tau. Okay, in the book, it's to my great regret. Okay, instead of calling it can't, because it's sort of it can't happen. You can't have a e of type. Well, you can have an open term of type 0. That's for sure. Okay, you can draw a contradiction from an assumption, of course, but you can't have a closed term of type 0. So the idea is I just call that. Well, in the book I called it abort, And then every student, and I don't blame them at all, every student gets confused because they think it means some kind of runtime error. And no, it doesn't mean that at all. That's not what's going on. It means that it cannot happen. So I greatly regret calling it that. So let's call it can't. Okay, so that can't happen. So you have this a limb form. The utility of it is that the utility of it is in connection with a case analysis. I'll just gesture at it. You have two cases here that both have to have the same outcome. Perhaps one of them cannot actually happen. All right, because of the typing of the considerations that are around, you can show that something is type 0. Then how do I achieve that I get something on this side? Well, I just say that can't happen. And I use can't to reconcile the types of the branches. That's what it's needed for, but only for open terms. It'll never come up. The gist of when you prove a type safety is that you'll see that you can never get a closed term of that type. So it's exactly analogous to reasoning by contradiction. And you do two cases, case A, case B, and case B, for various reasons in the surrounding context, can't happen. So you say, well, this one is, vacuously true. So this represents vacuity. Unfortunately, in the book, it's called a board, and in a sense, there's nothing wrong with that, but there is because it confuses everyone. So my mistake. Okay, so I shouldn't have done it. So 2 is 1 plus 1. So obviously, true is then going to be 1.1. Oh, sorry about that. Oh, excuse me, 1 dot the null tuple, I guess I called it, would be the element here. And false is going to be 2 dot this. And what is if going to be? Well, you know perfectly well what it's going to be. But I want to write it down because I want to mention the point I mentioned before. You do a case analysis, and in fact, there are two cases, each of which bind a variable. It's just that we know already the variable is going to be the null tuple, so why do we bother? Just call it _.e1 _.e2. The reason these are not evaluated is they're in the scope of a binder. It's not because of some magic about if. Okay? That's an erroneous idea that goes back to Lisp in 1960, for which no one can be blamed. But we should learn better now what's actually going on here. So we evaluate this, so it's really a binder. It binds a variable, but who cares? I already know it's going to be the null tuple. So that's that. So we can do that. So that's an example of what 2 is. And in fact, I can define any type n to be, this is an enumeration type, n copies of 1. So I can give them names instead of calling them, the first, the second, the third, the fourth, etc. I could call them A, B, C, D, and E if I want. Okay, that's fine. I can do that. All right, no problem with that. Okay, but in a lot of languages, commercial languages especially, they make a special hoo-ha about enumeration types. I don't know what's going on with that. Okay. The reason is that the issue is that the notion of sums in programming languages has been a bloodbath for decades. And finally, the commercial languages, as opposed to some of the research languages, are beginning to understand that things like the null pointer make no sense whatsoever. Okay? And the real issue is sums. Okay, so an example of that, a lot of you know this. Okay, if you look at like tau optional tau, well, that's just tau plus 1. It's tau plus the explicitly declining to provide a value. Either I provide a value type tau or I explicitly decline to do so. Straightforward. And with the recursion, then, I can do another one. And what I previously called omega, I can define to be, well, I don't have the option to write out infinitely many summands, so what I'm going to do is use recursive type. Okay, and it'll be rect t 1 plus t. And then, in a sense that I'm now going to explain, this is going to be, I'll use this very loosely because I don't wish to develop an equational theory of this language. But speaking loosely, this is going to be, so to say, isomorphic to 1 plus omega. That is that recursive type. What does it mean? It means if I take anything of this type, I can ask you, is it 0 or is it the successor of something? On the other hand, if I give you 0 or I give you the successor, I can turn it into a number. That's all there is to it. Now, in a call by name setting, we get to turn undefined things into numbers, but hey, we've already complained about that. Okay, we know that doesn't work. Okay, but the idea then is you say, so the gist of it is this, you say, if I take rect t dot tau and I plug that in for t and tau, then fold of that, that's the common terminology, I could parameterize it by t dot tau so you know which type operator we're talking about. And presumably Alexandra has talked about this kind of thing, type operator, so far from a semantic perspective, I think. But here I don't make any monotonicity or functoriality conditions. So I then say that this of E is of the recursive type, rect t.tau. So in other words, if I give you, just do it here, plug in omega for t, I get 1 plus omega. So if I take something in here, namely I tell you it's 0 or I tell you it's success or something, then I fold it to stick it back into omega. And then the way I get it back out is if you give me something in rect t.tau, then unfold of t of E is, well, the unfolding, the unrolling. Rect t.tau for t in tau. Okay, that's what we do. And then it has a dynamics. And the dynamics in the lazy setting is you typically say fold of E is a value. I do have the possibility of deciding to make that strict, but let me just do something for the sake of discussion. I don't want to reiterate the same issues I was speaking of last time. So we'll just say that that's a value. And then the other thing you do is you say, well, if E can take a step, then fold of E can take a step. Oh, let me write a little bit of abbreviation at the board. Okay, so we can do that. I'm sorry, I meant to say unfold. Okay, here's where the abbreviation happened. And that's supposed to say unfold. And then guess what? You know exactly what I'm going to do, okay, which is I'm going to say, well, if I'm unfolding something that has been folded, then that's what I get back. Okay, good. That's the core of it, why it ends up being an isomorphism if you work out an equational theory. It's just that you have to express the universal property of the solution to the domain equation, and I don't want to go there. So, but in essence, this is eventually what gives rise to this idea of an isomorphism between these two things, and let me just leave it at that. Okay, so from an operational point of view, it's that. So a nice way to think about that is with the following sort of pictures. So let's look at that. So I claimed what omega is. So what does that tell you? What is 0? Okay, by definition, then it's going to be fold. Really, I should write down t dot 1 plus t. And then it's going to be the in left, inject into the left, the null tuple. And if I want to look at the successor of E, then what is that going to be? It's going to fold. You're going to have to check now that this has the right type and it has all the right. You have to define all these things, and you're going to check all these things. So I do fold t1 plus t, and I put it in the right, and I put E in the right. And I do that. So the cool thing about it is that this formalism justifies box and pointer diagrams to a certain degree for a very simple data structure like this. Box and pointer diagrams are useless, okay? They are of no use, but why? Because they don't generalize for shit. As soon as you have any kind of higher order data structure where you have an embedded function, what box and pointer are you going to draw? And yet if you look in an algorithms book, I'm sorry to grind this act, they act like that's the whole world, like graphs. You know, they're all given there. What are you talking about? That's like, I mean, you know, I understand the utility of certain kinds of simplification stuff, but what's not acknowledged is what a simplification it is. And so that comes from, the origin of that is the machine models of computation versus language models of computation. And I wish I had some time to talk about that. In the supplemental notes, there's a discussion about this you might enjoy. You can have a look at that. Where, you know, in the machine models, the data's over there and the program acts on the data remotely. There's no idea of a program being part of the data. That doesn't even come up. So that's Turing's legacy. And Church's legacy is no. The entire notion of computation is based on the timeless idea of a variable and substitution. And that's what you learned in school when you were in X grade for whatever X is. You undoubtedly found it fun, like to mess around with polynomials and factor them and calculate with them is great, right? You're plug in. That's the origin of lambda calculus. That's where this comes from. They're two completely different things. The curious fact is how they cross, because the American guy, Church, is the one who influenced European computer science, and the European guy, or at any rate British, has influenced American computer science. And so I live in this kind of hell in a way, because the dominant thing in the US is always the kind of American, this Turing-style Turing machine. They always talk about Turing machines, but they have nothing to do with anything civilized, if you ask me. Nobody writes. No. Okay, so we're lambda guys, we know. Okay. So, not to deny Turing's brilliance, I'm not saying that, but I'm just saying. And then there's a horrendous tragedy of his life. But anyway, just the technical point about the so-called Turing machine, not the people, I think is not very useful. So then you have to figure out how you do if z. Okay, E1. And you can smell this. You know where this is going to go, right? Oh, so I was going to do box and pointer diagram. It's sort of an abstract pointer, I'll draw it like that, to a labeled piece of data saying, oh, I'm on the left-hand side, to nothing whatsoever, which I can write like that. That's my 0. And if I look at the successor, then I say, oh, you're a successor, by putting a 2 here. And then I have an abstract pointer here, which goes to the next guy, who knows, maybe it's 0. And then that's a picture of 1. Okay, so you can do that. So the recursive types give you a quite close analogy. It's just that it doesn't scale. As soon as I start putting in more interesting types here, well, then that whole business goes right out the window. Okay, but you can at least mention that. So what happens is unfolding is chasing the pointer. That's the star, if you want to think of it like that, in C. Okay, and then you want to look at the bit pattern. And then languages like C don't have sums. That's all of object-oriented programming is based on not getting sums correct. It's a complete train wreck, okay? So you can't summarize here. But anyway, you do a case analysis on which one you're doing, and then you branch according to that. So that's how if z works. So what do? I do a case analysis on the unfold of E. And in the first case, well, I already know what comes. If it's actually a 1, then there's nothing there. So I'll just write E1. That's why it's written like that. In the second case, I need to know what the predecessor is. Let's call it X. And then I just have E2. That's all. So it just says chase the pointer, inspect the bit. It happens to be a bit here. I just have 2 cases. And I do that. I can have any number of cases I like. So I can write it like that. So that's a fundamental notion of how we get some things in recursive types. Okay. All right, so now I want to do the interesting example, which is how you derive self-reference in this setting. Okay, so this seemed reasonably okay. The thing I want to point out, maybe I should point out, well, it's going to come up when I do this example, so let me just do it en passant. I emphasize, although this example does fall into the pattern of defining a monotone type operator in an appropriate sense, or positive type operator, that's not necessarily the case, and that's what I'm going to do next. And that's where all the action is, okay? That's where all the action is. That's where things happen, okay? So what I'm going to do is the following thing, is I want us to understand what is going on with self-reference. And the key idea is, this can be done, I'm going to do it in a very direct way. You can also do it in an indirect way via encoding more general untyped mechanisms, but I'll just do it in a direct way. The key idea of self-reference is self-application, so I'll show you what that means. This is, if you look at introductory textbooks, this kind of thing is another thing that I think is not so well explained, and I'll show you why I say that in a second, okay? And as I mentioned yesterday, this is Kleeni's idea. It comes from Kleenie and Church, and before computers even existed by quite a while. So I want to explain how that is. Okay, so how do we get self-reference? So the critical idea is I want to consider the following thing. So let's look at a type. I'll call it tau self. And this is going to be the self-referential. I want it to be a type of self-referential, well, it'll be computations in this setting because I'm working by name, of type tau. Okay, so as an example, okay, if I look at the standard thing is some factorial function, we're going to expect, you can think of the factorial function, which is some piece of code we're going to be able to write down easily, and it's going to be a self-referential function from omega to omega. That's what's important about it. Okay, that's what we're going to do here. So we're going to distinguish in the type a self-referential thing. If you want to cover up that distinction, you can. I'll show you how to do that. But in the first moment, we prefer to keep let's be explicit about it. So I want to distinguish a priori the idea of self-referential thing. So I want to type tau self, and a lot of you know how this works, but I'll re-explain it to you, and it's entirely a clever hack. I mean, that's it. It's a clever hack, okay? How do I achieve maybe some of you know, maybe some of you don't. I know that when I teach, like, second-year students, from what they learn in the first year, they don't quite ever get the idea. And in fact, and particularly if you had the misfortune of being taught, like, Java or something, you have this ooga-booga about this. Jesus H. Christ. I mean, it go on and on and on about this, and people think it's some special thing about object-oriented programming. It has nothing to do with that, okay? So what is the idea? Well, suppose I want to just think of like as a hacker, okay? You want to write a program that refers to itself, it calls itself. How are you going to do that? Well, one method that people use is they resort to embedding things in memory and use addresses and stuff like this. So let's not do that. Let's be civilized, okay? So we want to have some way of writing down a function that refers to itself. Well, what you do is you introduce a protocol. And the protocol is that here's what I'm going to do. I'm going to give the function an extra argument, okay, which I'm going to arrange by convention will always be the thing itself. And that way, when I want to call myself, I call my implicit first argument, but I'm going to arrange that it will be the thing itself. And now you've done recursion. Boom, done. That's the entire thing. That's the Y Combinator, and that was invented by Kleene. So let me show you how that works. So what you do, and now here's the fun part. This, by definition, is a recursive type, and the type is T partial arrow tau. I'm not limiting myself to functions here, because in particularly in the by name setting, it's very natural to allow it for any type at all. But so, for example, when I was building gates, I was giving you a self-referential Boolean. That was the computation of the gate that I gave you in the first lecture. So here's the thing. Notice that this is a negative occurrence, so-called. That's the terminology, a negative occurrence of T. So this is not monotone, it's antitone. It would be a contravariant as a functor if you want to think of it like this, okay? Notice the way I'm defining this. I'm implicitly using binding conventions. T can't occur in tau because it's given from the outside and I have a bound variable, so it's different from anything. So tau doesn't have any T's in it, okay? So the critical idea is even if I'm doing a self-referential Boolean, if that's 2, which is defined like that, whatever, then what I'm doing is I'm saying it's a rect T arrow 2, okay? So it takes an argument, even though it seems to be a Boolean, precisely because it's self-referential, because that's how I tie the knot, okay? That's what's going to happen. So what do we do is I want to say, what is the intro form? Well, I want self x.e to be of type tau self when, forgive me for writing my rules upside down. When assuming it is the tau self, I get that it's a tau. That's what I want. This is like, I want to define this, and it's going to have a certain dynamics, which will be explained when I define the next thing. Okay, so I wanted to do that. Because a self-referential Boolean takes as input a self-referential Boolean, which is going to be the thing itself. That's why it's a self-referential thing. And it tells you a Boolean. Or if you're looking at factorial, it takes in a omega self and gives you back an omega arrow omega. That's the body of the function, okay, defined in terms of a reference to itself. Okay, so that's the idea. So how do we define that? So we define self x.e to be, by definition, what is it supposed to be? Well, this is a recursive type, so it's going to be a fold. Oh, if you don't mind, I'll not write that. Oh, I can write it out. Okay, T arrow tau. Okay, good. I did that. And now what does it take in as argument? Well, if you look at the fold is going to take in an argument of tau self arrow tau. So if you don't mind me scrolling, the domain of this function will be a tau self, and it takes in x, and it gives me back a tau. And I'm done. That's the definition. Okay, so that's the simple thing. And then the next thing we'll show you how the protocol works. Okay, so what we do is we fold. So just by typing consideration, I just followed my nose and said, oh, make the types work out. It must be the right answer. It will be, but anyway. Okay, so I'm pretty sure if I didn't make a mistake, assuming x is a tau self, e is going to be a tau because that's what I'm given here. And then I say, okay, so therefore this is a tau self arrow tau. That's the unrolling of the recursive type, so when I fold it, I get a tau self. Yeah, so I think I did that right. Okay, so that works. And now what is what I want to define is I want to define what I'll call unroll. You explicitly unroll the recursion. Okay, so what I do is I say unroll of e. And what is that guy going to do? This implements the protocol. See, the idea is that if you think of that as the body of the factorial function, maybe I would have called that variable f or something, but anyway, whatever I called it. Maybe I call it this. Okay, so I could call it this. Okay, whatever. Okay, so call it this. So the point is that inside of here, it refers to this, but this is nothing else but a parameter of this function. There's no idea that it, in and of itself, that it means the thing itself. That's arranged by the protocol. And the protocol is you unfold things. You unfold E. So it started out with type. So the idea is that this is a tau self, and therefore I want the entire unroll to be a, whatever it's supposed to be, a tau self arrow tau. Oops, yep. It's a tau self arrow tau. Okay, that's what the unfold gives me. So I want, so that the rule that I want is that if this is a tau self, what unroll is a tau. And how am I going to do that? Well, if I unfold it, then its type is tau self arrow tau. It's something that takes a thing which I'm going to arrange to be the thing itself, which I bloody well will do with E. So I have an implicit argument, I pass that in. Okay? So this is type tau self. This is a function from tau self to tau. This guy pretends that it's calling itself by referring to x, and then I make the pretense come out true. I avoid embarrassment, okay, by making the pretext come out true. You see it? See what I'm doing? Is that okay? I'm not sure whether this is totally dead obvious and you wish I would move on, or whether you're not quite sure. I need to distinguish between those two things. No question? You're all okay with that? Okay. So this is called self-application because modulo the unfold, I'm applying E to itself. And as a matter of fact, when I do what I'm going to do in a couple of steps, that's really what literally will happen. This is the magic of the Y Combinator. You might know the Y Combinator. If you know the lambda calculus, by definition is lambda x, f applied to x, applied to x, applied to lambda x, f applied to x, applied to x. The heart of it is the f applied to x, applied to x. Okay, that's the heart of it. The mystery of it is entirely revealed here. That's the idea. And Dana's analysis of the untyped lambda calculus in terms of recursive type is what allows me to bring this out clearly. Okay, so that's I hope clearly. My intent is bring it out clearly. Okay, so that's it. That's how you do it, and that's how you get self-reference. And now, okay, so how do I get fixed? Well, it's just a matter of unfolding, doing one additional unfold. Because what I do is, I need a place to write this. So what I did here is I was a little bit finicky, and it's a little bit finicky, but the idea is that, well, suppose I define some f, which is, let's say, I don't know what to call it. Let's call it up, which is some kind of tau self. So let's do it as an example, something like factorial. So I give you a self-referential function on numbers. How do I call that guy? Well, the way you call it, the way the version of apply is, if you're going to apply a self-referential function, so call it, I don't know, self-app or something, then what I do is self-app f to E. Then what do I do? I'm going to define that in the following way. You unroll f, which is self-referential, and apply it to E. All right, now let's E to expand this thing, get rid of that. So the idea is that if you take unroll of f, its type is omega arrow omega, and then you just apply it normally. This is apply unroll of f to E. Okay, and that's what I do here. So unroll turns the thing that it starts out life being explained as a self-referential thing, and you just unroll it, now you've got a function. You've hidden the fact that it's self-referential, I can just apply it. And as a matter of fact, the way I do the recursive calls inside the body of factorial, I don't just apply the implicit argument this. I don't just apply this to x minus 1 or whatever you want to say. I say unroll x and apply it to n minus 1. But then unroll of thing to n minus 1 is exactly, the use of the unroll of the factorial function without the self being revealed. And then it's all the same. Okay, so that's how that works. So that's the story. So unroll of f turns out to be unfold of f because it's self-referential, and then apply it to itself. So that way, the fiction, so to speak, of the first argument, the thing called this being this, is made to come true right here. And that's the whole idea of self-application. Boom. You don't need any pointers, you don't need any memory, you don't need any. It's like, that was the beauty of what Church invents in 1932. Okay, so that's, in my mind, a very remarkable achievement. There's the eraser. Okay. All right, so that's what I want to say about that. So that's how we derive fixed. And now I want to say a couple of things about what happens when we do this in a call in a by value setting, because it changes things a little bit. So I'm just double checking for myself. Okay, yeah, change things. Maybe we can take a break. This would be a good moment for a 5-minute break. Why don't we do that? And then I'll talk about the by value setting and the universal interpretation. Okay, good. All right, thanks. Limitations of time. So I'm not positive. I may overflow into the next time. I'm not exactly sure how this will go, but there are a couple of points I want to make, so let me continue with that. Okay, so is this reasonably okay? Obviously, I'm sketching, but there is a backing store, so you can look these up. Someone's asking me for references. Many of them are in the book, in the PFDL that you can get. It's online on the webpage I mentioned. Yeah, okay, you can look there. And, okay, so... Oh, right. The other thing I wanted to say while I have a moment, I guess from what I understand, there's a study session, and it's at 4, question mark? Is that right? Does anyone know?
Yeah.
I'm at 4 o'clock? Okay, whatever time it is, I'll show up. I'll be here. So if you want to discuss further, I'm happy to do that. So that'll be fine. Okay, so I hope you'll come to that. Okay, I think the other faculty will be here also. So, I mean, we'll just I don't know what we'll do, but we'll figure out ways to converse. Okay, so good. So, right. All right, so that was the by name version. I wanted to explain carefully about why I obscured it. It's over here. I felt I owed that to you. Plus, it's in a certain way the cleanest thing because it connects up very nicely with the lambda calculus. It's a very nice way to do it. Let's just mention that there's also FPC by value. The previous one would be by name. Okay. And the main ideas are the same. Ideas are as for our PCF by value, let's write PCFV, which I did yesterday, which I was talking about yesterday. But let me mention a couple of points anyway, okay, that we can do that. So as there, we have a distinction between values and we have a distinction between computations. And I guess I have to say a few things, so I will say it. So things like the null tuple of a value, a pair of values typically. So therefore, this would correspond that when I started counting to parallelism, then I wanted to emphasize the idea of a pair of values, and I wrote it this way because I wanted to have two different products going at the same time. I can incorporate everything I said yesterday into the FPC. It all scales, but I obviously can't do that for pedagogical reasons, so you just have to believe me that it scales, and I'll just, cut to the heart of the matter here, okay, so we can do that. So we're going to have this that sort of setup. So that's the correspondence there, but I'm not going to broach parallelism. If I were, then I would have the idea of a pair of two computations, but let me not do that right now. But I do have, in this setting, I do still have, comp of M, so I have a suspended M, and then we're going to talk about how you do the self-reference. It's kind of the same idea, it's just a little bit more involved. Okay, so I have a comp of M, and then what other values do I have? I have 1.v and I have 2.v, because I'm working in a strict setting. If I want to make things lazy, I just use computations. And sort of that's the whole heart of the matter. If you want to have, for example, a data structure that exists only on demand, like a stream or something, that's a typical thing people tell you about. I believe Alexander was probably talking about that, and some other people will be talking about that. If you want to have a data structure that exists on demand, what does that mean? It means that the data structure is given by a piece of code, and it tells you, about the implied data structure given by that piece of code only insofar as you look at it. Okay, so every time you kick it, it'll say, it wakes up and says, the next element of the stream is 7, then goes back to sleep. Okay, so the way you mediate that is using computation types, suspended computation, good value, but it's just saying, well, this is the programming language analog of TBD, to be determined. Okay, so this is how you do to be determined. Okay, it's that. Okay, so that's what gives rise in this setting. That's how you deal with data structures defined by their elimination properties, like looking at them like stream, you look at the head and the tail. Okay, as opposed to their structure, they have mapping in property rather than mapping out property. Okay, so we have the summands. Let's see, what else was I supposed to do? Conveniently, all my types are up here, so it reminds me. Okay, so I do this. And then the body, as we said, was M, or else I can insist it be E, and then you can put a computation marker in there if you want, as I was saying last time. If I don't feel like forcing that on you and let you use partial functions, then I'll just write it like that. That's a detail, like we can do that either way, okay? So we can do that, and I have fold of a value. Because you see, with the fold of E, in general here, in the call by name setting, I'm able to smuggle in a pointer to nothing whatsoever, something that's undefined. There's something fundamentally wrong by that. But if you think of that as fold as this abstract pointer, this could be something divergent in it by name setting, so you have a pointer to nothing. Okay, so that's what happens. Here I'm insisting that it be a value, so you can only have a pointer to something that actually exists. Okay, so that's the distinction between these two things. So the same thing happens here. So I do fold. I'm pretty sure that's all I need to do right here. And and of course, variables I'm going to have. If I'm doing the syntax, I'm going to have that. I could write all the typing rules. I'm going to assume a little bit that you can fill in some details. Okay, so that's what we do there. And what do we do about computations? Well, if I want to be finicky, I'll say return a v, or just v, then any value is computation. I'm going to have, as before, bind v x.m, which is sequencing. Of course, that can be generalized to parallelism, but let's leave that aside. Okay, so I can do this, and I can also put in the Benton-Kennedy exceptions. I'm just not doing that. And let's see, so I want to do that. And then we have to decide what we're going to do about our limb form. So I could do a split if I do a product. Okay, so I will have split v, x1, x2, m. All right, and then I'm going to have case. We'll go here. If you don't mind, I won't write that out again. And then I could have can't here, okay, of v. Okay, so v could be a variable if it's an open term. Otherwise, it's not going to be a closed value. But anyway, it's can't of v. It's already been evaluated. What you're doing is the way to think about that. Okay, but it can't happen that this will be a closed value. Okay, and then what else do I need to do? Application. If you do it as a partial function, then application would go here. You'd say apply v1 to v2. If instead it was a total function yielding computation, then you could still put application here because it does some work. Or, as I mentioned, you can, instead of having things that are merely values, you could have things that, well, are tantamount to values, that will evaluate to a value briefly. Okay, so we can do that. There's choices to be made here, but I can do that. Okay, and then unfold is important. If I haven't forgotten anything, then unfold. Okay, v. And that's a form of computation. Why? Because that can engender things to happen. Okay, when I unfold things, I plug something in. I have what I'm going to end up with. I'm going to have, and what are the computations? I forgot to put up here on this one. No, I did. I put it up here. Yeah. So we have an encapsulated computation. So we do this. Okay. So we have unfold here, in the same kind of reason why app is here. Okay. So we can do that setting. Now one can write out the typing rules, and they're expectable given what we said last time and what I've said earlier in this lecture. So the only thing I want to mention then is you can then replicate the entire story about self-referential things. I just need to be a little bit more careful. So what I do before, so for example, if I want to do a tau self, one way to do this is I can think of this. We're going to, I have the type tau self, so I want to have a particular, what is tau self? Let me write that out. Tau self is as before, okay, by definition. Okay, rect t. I'll now write it as tau comp because I'm gonna use a total function formulation of it. I can also do it the other way, but I just want to make a point because of how we're going to deal with self-reference here. So we're going to do the same thing. So the critical thing is what I did ad hocly with comp x.m, where I give a self-reference. That's the self-reference. And otherwise, it's the exact same story as before. So these things now look very similar. The only thing we have to worry about is what does it mean to do self? And now the question is, what do we do here? So it's really going to be x.m. So that's the important point. I believe that's what I set up here, right? Okay, and that's going to be a tau self, and I want that to be the case when, assuming x is a tau self, that's a value, then m is weakly of type tau. That's the difference in the setting. Okay, because when I unfold it, it's going to work. It's going to do some work. Okay, so it's only weakly. Okay, weakly of that type. So the question is now, how do we define that thing? Well, that part looks exactly the same. And I will write that out here. Okay, and then what I'm going to do is I'm going to do really the exact same thing. It doesn't look different at the moment, except for one thing, which is since I'm insisting on this idea, then I put here comp of m, okay, because I'm having a function that goes from tau self to tau self comp, or tau comp, excuse me, and that's a weakly of type tau, so comp m is strongly of type tau comp, yep. So the typing of that should work. And then the only thing you have to worry about is what happens with unroll. And now that's a little bit thing. So this is going to be a tau self, just like it has before. And I want this whole thing, I'm going to have it be weakly. That's what's going to happen here. I'm going to have this be weakly of type tau, I guess. Yep. Okay, so I'm going to do that. And so how am I going to do it? Well, you can just follow your nose. Like you can sort of say what's going to happen here. Well, now what I have to do is I have a tau self, okay? So as before, I want to unfold this because that's a recursive type. But an unfold is a computation, so I have to say, let's first of all unfold the computation. So what I do is I bind this unfold. This is an idiom, okay? This is an idiom here. I shouldn't have called that E, this should be V. I keep making that same mistake because the unroll is defined, it's already, the arguments are, unroll will be taking a value in the same way that unfold does. So this will be that. So this is an idiom here because bind is the elim form for the computation type, so I just take that thing, turn it into a value, and do bind. You can make a defined form in which you don't bother with that. I'm not too concerned about that. This is just an idiomatic thing, a little clumsy, but idiomatic. So I unfold that thing, and then what do I get here? So when I unfold this guy, it's going to be, what is it going to be? It's going to be a tau self error tau comp, right? So the idea is that this type will be tau self arrow tau comp, if I'm not mistaken, because I define tau self in this way. Yep. So I think I'm good with that. So that's what that's going to be. All right. So when I do it, it's going to be, so I do an unfold of V, it's going to be weakly that, okay? I'm going to run that thing and figure out what its value is, and that's going to be here, and it's going to be this type tau self arrow tau comp. Okay, so that's what I'm going to do. Now what I want to do is if I'm going to be weakly of type tau, then, so if I want to be weakly of type tau, then what I have to do is bind the application. I take the application of X to V. It's not so immediately obvious that it's self-application anymore, because what I'm doing is I'm taking the original thing, which is a tau self, and X has been run, and that's the value of this computation. It has this type, and I'm applying it to tau self, and the protocol will arrange that it be itself, but it's X to V. Okay, so that's what happens here. You bind that, you take your thing, and you return that. Okay, and if I did that correctly, it will have the type computation of tau. Okay, so that's what it looks like. And it looks a little clumsy, but I say there are many, you can do surface syntax things that make it perfectly pleasant. And so, for example, in Haskell, you have the so-called, I think it's called the do syntax or something like that. It's sort of a nice way to write these things down. Yeah?
I have a question about the definition of the term self.
Of the term self?
Yeah, so the body of the lambda is comp m, right? But that's a value. Shouldn't the body of the lambda be a computation?
This is self x.m, so I think what I'm arranging is self-referential computations.
Uh-huh.
Okay. If I did this all right, I wrote this out last night after picnic. So I think this is right. So I'm defining, this is my choice. I could have a self-referential value of type tau comp if I want. So given this, you can do what I did yesterday as an exercise, where I have a self-referential value of type comp, of tau comp. Here I'm just saying a self-referential tau.
But I feel like the right-hand side is not well formed.
The right-hand side is weak, is what I'm doing it here.
Yeah, but you have lambda comp m, right?
Lambda of
comp m on the right. Yeah, of the term. You say is equal by definition to full of lambda comp m.
I don't need it. This is what I wrote over here. Is that what you're asking?
Yeah.
Okay. Oh, I see. I did the wrong thing. You're right. Yeah, so I guess what I should have, it's an impedance problem. I decided to write it like that. Okay, so I could have instead written this. I'm sorry. Now I get your question. I'm sorry it took me so long. I could have been t partial arrow tau, but I wrote it out as t arrow tau comp. The reason is I wanted to make explicit here that I have to do this. Okay, so that's the thing I wanted to do. I could have done it a different way, which is instead of making it be a tau comp, I could have said t partial arrow tau. Then I would have had to bind a comp of the application and then return that. I mean, or I could, but then in that case, I could just use the application. There are different ways to set it up. It just depends on how you want to set up the induction. So a lot of variations you can do here. Okay, but let me leave what I wrote. Maybe it was ill-advised, but I wrote it like that. Therefore, I had to turn the computation into a value.
But the body of the lambda is already supposed to be a computation, right?
Okay, can I say return?
Okay, cool.
Okay, if it's a partial function, yes. If I have total functions, the body will be a value. So I'm sorry, didn't do a great job here. I could have written x.v here and demanded that for a total function, the body be a value, and then I would have been fine with that. Okay, if instead I have a partial function, then I probably didn't need the comp anyway. I could just said m. Okay, so it's a balloon squeezing exercise. Where are you going to put certain information? That's all. Okay, that's all I'm doing. Okay, so then it's a little bit more stilted looking, but anyway, this is the same idea in that setting. Okay, so I'm going to leave it at that. I think I didn't have any other extremely important points to make there. No, I want to make the point. Okay, yes. Oh, Penn, thank you for telling me that. Okay, so let me just leave it at that. I just want to say that this is roughly how it's going to look. That's what happens to you. This is how these things work. Then, as I alluded to earlier, then I can start doing things like recursive types, like something that looks like a stream might have a type that looks like rect t, and it's going to be a computation of, maybe it's a stream of numbers. This will be a computation of maybe a natural number and another t. Okay, something like that. So when I unroll it and unfold that and bind the result of the computation, I'm going to get a number, which is the next thing. And maybe if you want to have it possibly terminating, then you can put +1. I don't care. Okay, or you can make it be infinite. Okay, and then you get the omega, and then you get another computation, such computation. So the comp media is the spots where things are going to be delayed. And so it's kind of nice because the type is telling you where things are going to be delayed. It's not like foisted on you. Okay, so that's the thing that is kind of useful about thinking about this way, I think. Okay, so that's the kind of thing I wanted to mention here. So that's what happens to you. You make explicit the use of delaying. Okay, good. So now the last thing I want to say is about this remark about untyped and unityped. And the gist of my remark is that languages like the currently most popular one is Python, but whether you realize it or not, Python is literally 1970 Lisp. Okay, do you understand that? It has deliberately remade all the same mistakes that were made in 1970, which were completely forgivable in 1970, but are not forgivable in 2020 or 2019. But it's exactly the same thing. Okay, so the idea there was always that somehow once ideas about types started to come into play around 1980, it used to be a time, you'll laugh, but when I would give a talk at Poplar, you had to apologize for writing types down in inference rules, and you had to explain what inference rules were in a Poplar talk because everyone was either hostile or ignorant. It was very different Poplar than it is today. So the world has completely changed. But at that time, there was a hostility. And the idea was to say, put everything in one big pot. So the idea is you have one big pot. That's the way I'll put it. One big pot, which is a single, the word universal is a bit of a stretch, but the terminology exists of a universal domain. So one universal type. So the idea is that if I write it down as syntax, it has a certain appeal, and I'll write U. And in the book, I don't have time to develop it here, there's a systematic development of this that you might enjoy, because it really, if you're not familiar with this thing, the example I worked out there really shows you what's actually going on. I'm going to give you a hint about this now. So I'm going to have a notational problem, okay, and I don't know what to do about it. I never know what to do about it. But we're going to have some idea of what are the untyped terms, and we're going to have something like, okay, the number n, okay, that I don't know what to notate it as, like what the concrete syntax is, but I want to sort of think of it like this. So we're going to have we have some things like this. Often there are things that are built in. So there's things like if 0. It can be, many things are variable. You just have to trust me that I'm not rigging it in order to make my point. It doesn't matter. You do it any way you like with putting everything in one pot, and the same story applies. Okay. So you just take my word for that. Okay. So I can have U1, and I can also have x.U2 here. So the U is emphasizing it's untyped. So you don't have anything to do with type. So the idea is that anything that parses works. Okay. Anything that parses will do something. So that was a great thing about Lisp in the old days. Whatever you typed in, as long as the parentheses matched, something would happen. Okay? And then, to be a little sarcastic, that made it AI. Because, you see, who knows what it's doing? Nobody understands that. Well, it just does whatever. And that was like a feature somehow that you couldn't understand what was going on. But Drew McDermott, who was a professor at Yale at the time, wrote a paper about that. You can look it up. Okay, but okay, so this is the conditional. Okay, and then I can write other things here. So the typical thing was to have what was always called nil and cons. I don't have to do this, but what's going on here? Oh, that's the null tuple morally. That's the thing that corresponds to that. This corresponds to having an ordered pair. Okay, and we can do a whole bunch of things. So I just want to give you a flavor. And then the book gives you a lot more detail about what's going on here. So you get a programming language that looks like this, and then anything that parses, there's no point. The only thing you can say is, if you want to, by way of a statics, and they don't even do this, and the reason is that in Lisp and also in Python, they're all confused about what variables are. But let's pretend they're not. Let's say that this is scheme, which is reasonably well-defined thing. Then the statics amounts to saying, I'm just stipulating what are the variables. Or I can just write that term, or I can just say U is okay. And that just means all of its free variables are amongst those given. That's the entire static semantics. The only thing you care about is what are the scopes. In Lisp and derivatives, the notion of scope isn't even done properly, so it's a complete mess. But here's a reasonable version of it. Okay, so you do that, and then you have a dynamics, and it's going to look a lot like what you might want it to be. You know, you just write a transition system like this, and you have U as a value. You can write this down in the same spirit that whatever you do. But you do have a problem, because besides U value, you also have to have U error. And the reason is that I can do things like, I can write down, this parses, if Z nil, U1, X, U2, and what is that supposed to transition to? Well, the way I'm setting this up is that's not a number, and so since that's not a number, the only thing I can say about it is it's erroneous. Okay? So what you do when you write code this way is that it's extremely pleasant to sit there without knowing what you're doing and type in a whole bunch of stuff and it seems to do something. But good luck, down the road, what happens, some error pops up, well, you just end up with this steaming pile of Python code that nobody can maintain. Okay, that's what happens. It's a regrettable state of affairs. There's a tension between the pleasant, immediate feedback of something or other sort of works versus knowing what you're doing. Okay, and knowing what you're doing requires a little bit of advanced planning, and then there's always a resistance to advanced planning for some reason. Okay, but it's never other than regretted. Okay, if you don't do it. Okay, but anyway, that's that. So you do this kind of thing. So you have to have a notion of an error. So where does this come from? So the key idea is this. The key idea here is that there's really one type. There's one universal type. Oh, that's what I said up there. Okay, so I have one universal type, and what is that? Well, I'm going to have a recursive type, T, and it's going to have clauses corresponding to all these various forms of data, and these are the classes of data. Okay, and so we do this kind of class checking. So I'll write it using the labeled form because it's easier. So I'll say the class of nils, there's exactly one nil, the thing that has no interesting data associated with it. It's 1, so this is the summand. There's the class of consas, which consists of pairs of T cross T. Okay, like that. There's the class of functions, which consist of, let's say, partial functions from T to T. And you can have a class of numbers, where the associated data is an actual number. And well, keep going. okay? So what Dana did is, let's forget all this other cruft. If you just focus on this one clause, Dana's model of the lambda calculus amounts to the recursive type rect t partial error t. And what makes it a little bit remarkable until you understand more deeply, well, it's remarkable in any case, but on the surface, particularly if I wrote this using a total arrow, you think that can't possibly make sense because supposedly that's isomorphic, call that D. Supposedly that's isomorphic to D arrow D, and we know that in sets, that's only possible with the trivial 1 point thing. Okay, there's only, okay? So what's going on? How can I get a non-trivial thing? Well, the reason is that he considers continuous functions with respect to appropriate topology, and that's the key idea. Okay, and it's called, oddly enough, it's called the Scott topology. Okay, so you can follow that down. So that corresponds to considering just the one clause here, okay? Because that was all you needed for the untyped lambda calculus. And what these other languages are is like a jazzed up version of the untyped lambda calculus with multiple classes of data, not merely functions, okay? So this is the setup, and this is my universe, let's call it capital U, I don't know, capital U here. And then what OK means is OK means that it inhabits the universe under the assumption that the xi's inhabit the universe. So I have a bunch of those. That's what my statics means. Now let's look at the dynamics. This is where it gets ridiculous. Okay, so yes?
Well, you said topology, but I think I was before that. What word, what topology?
Can you repeat what
Like what topology?
The Scott topology, I was making a joke. The thing that Dana invented, oddly enough, the topology in question became known as the Scott topology. So, okay. From a geometric sort of point of view, it's a very weird thing, but it's a perfectly sensible idea, and it influenced a lot that came later. So what was I going to do? Oh, so now when we look at the dynamics is where we see where this error business arises. Because what we want to do is, all right, so now let's look. So what is nil really? Okay, if I look in terms of this underlying, this universal type, well, it's a fold, which means in an abstract sense, it must be represented by a pointer. You're already in a state of sin here because why are you doing this? Because the same thing's going to happen with a number n. It's going to be a pointer. Okay, and I'll say what it is. What is it? It says I'm in the class number and my underlying data is n. That's the so-called instance data of that class, if you want to say that. My underlying data is n. Here, what am I going to do? I'm going to be in the nil class, and my underlying data is just going to be trivial. And then what do I do with cons? Well, now you know kind of what I'm going to do because you see these are constructors for the class. Oh, I should call it U1, U2. Okay. So what do we do here? Well, that's a fold. And you're in the cons class. So you say I'm a cons and I consist of a pair of U1 and U2. Okay. So now let's go back to our box and pointer diagram, just pausing right here. It means I have an abstract pointer to a labeled thing. And it means that all the elimination forms now have to check whether the label works. So how does if work if we do this? I'll just erase right here. So how does if work? Well, what happens with if is, if I look at this, what do I do here? Well, first of all, let me simplify and just work as if I'm doing by name. In reality, such languages are by value, but then I'm going to have to write more code. So let me just do it simplified. In the interest of time, I'll write this down. So what I want to do is I want to say, I have to unfold this thing. So unfold U. So I get that. So an unfold U is an element of the big sum type, which tells you all the classes. Now I have to have a case for each class. So if it's the numeric class, then I don't care what this is, it's an error. I have to have some way of signaling an error. That's an exception, basically. All right? I could work exceptions in, but I'm just like, allow me to have them. Okay? I go all the way down here. I'm trying to do if. So, if z. I was trying to do if z. So number is exactly the one I want. So I set it backward. So if it's in fact a number and the number is x, okay, then I'm going to do an actual underlying if z. So now that's where my notational problem comes in. How about if I call that if z in capitals? because I need to distinguish this. This is the external syntax on working on untyped terms. So what I do is I unfold it, turn it into the typed world, now do the real IFSI, the real Boolean branch on X, and then I want to be U1. And then we have to be careful because I'm going to bind the predecessor, you see. But that's an actual honest-to-God number, and that's not what I want. What I want to do is I have to now fold this guy and mark it as being a number, okay? And then I have to plug that in for X, I called it, in U2. Oh, does that ever stink? Okay. Moreover, I have to have these other case analyses. If you give me nil, that's an error. So I have to say _.error. I have to have an error mechanism. And I have to do that for, and I do that for all the elim forms. And moreover, this is really quite important, is that I take the predecessor of a number and I must remind the implementation, I must make explicit in the runtime data that the predecessor of number is an actual number by doing an allocation, which is a fold, and labeling it and putting the X prime there. Well, guess what happens when you're going around a loop? Well, you know, a number of years ago, my students entered the ICFP programming language contest, and you know, they wrote in a semester an ad hoc compiler for a fragment of ML, and then they compared it to the commercial Python code, and it was 3,000 times slower. Okay. It's kind of ironic because, you know, in the history of programming language, what happens is the history up to that point was, oh, efficiency was paramount. We can't possibly have higher functions, anything like, no, efficiency is paramount. Then suddenly everyone loves Python, which is thousands of times slower than anything natural and useful. And yeah, oh, but then suddenly it doesn't count anymore. And it's like, things matter of the utmost importance up until exactly the moment that they're not. Okay, so that's a frustration I've experienced. So what happens is, there's a hell of a lot of overhead here. Now, what I don't have time to do with you at the board, so you can get an idea, so you can start writing it out. This is where the runtime error goes. All the numeric calculations are mediated by these ridiculous foldings and markings and taggings, and you're constantly checking tags and putting them back on. Then you can do something, you can say, okay. But insofar as I can see the entire program, the issue is modularity. If things are coming from the outside, you don't have any choice. You don't have any control of what's happening. But maybe inside your loop, you can do some optimization. So in the book, what I do is I go through and I tell you, okay, let's write down some loop invariants so that I can try to improve the code and optimize it. What pops out? The ML code you would have written in the first place, which is perfectly well typed, wrapped around the outside with one single fold and unfold. Okay, so what is the argument? Why didn't I just write this in the first place? I don't know. Okay. To me, there's no sensible argument, except the juvenile argument that says, well, anything I type in does something. Isn't that great? Okay. All right, so we can teach that to fifth graders. All right? But if you want to be serious, like you want to know, like, what are the invariant structures, what's going on with the code you're writing, you want to write down the types so you know what you're doing. And the premise, then this kind of exposes what happens when you don't, is that the overhead that you're imposing is all this tagging and tag checking that's going on. And in the book is a worked example you might enjoy going through. And then you just see, like, you know, there was no advantage to this, particularly once you know about type inference. Because then literally you write an untyped term, meaning I do not write any types down. The compiler figures it all out. But it's all typed, and we don't have all this overhead. It's a pure win. So to me, it's like outrageously retrograde, okay, to go back to 1970. I don't know why we're going through this exercise, but for some reason we are. And so this is a way of, like, understanding, at least conceptually, you can understand what's going on. So you can get a flavor of why a student compiler written this semester, you know, the factor would be like of 3,000, and they weren't even half serious. Okay, so it's like, that's what happens to you. But somehow that's good. So, all right, seems to be. So that's the flavor of it. And then you can go through these examples and you can see how to do the optimization, what it means to do data flow analysis so that you can carry out, so you can try to eliminate these these kind of overheads. And you can do that to a degree insofar as you're not appealing to separately compiled code. As soon as you have modularity, then again you have the overhead and you can't avoid it because you don't know what's going to be plugged in. So that's what happens. So these things, it's kind of nice looking on the board, and it's kind of nice that you can just sort of type something in. But if you look at what's really going on, you have some sense of what's happening. Then the story is really one of recursive types, and then this is what is going on. And once you understand that in detail, I would suggest you probably have the same reaction I have, which is why that's absurd. When I showed this to a graduate student a number of years ago, it happened to come up in the case of Java, because the same thing in Java. It's called object, okay, but it's the exact same thing. And I pointed out what was happening there, and the student was like, no, absolutely not. And I was like, it has to be. So he went and looked at the bytecode, and he came back to me white-faced. It was like he could not believe that this is actually what was going on. I was like, I told you. Okay, so it has to be, because this is the logic of the situation, as it were. This is the type theory that's going on underneath it. So in a way, this is a worked example. At the very least, the type theory kind of tells us what's really happening. That's the ground truth. And then, things are, built on top of that, and you can choose to like them or not like them. Okay, I have my opinions and I express them, but everyone can have their opinion. So you can like them or not like them, but anyway, this is what's happening. That's the important point. Okay, so that wraps up what I wanted to say about recursive types. Jan wanted me to do that so he could use them. So I hope I've covered what he wants me to cover. Okay, so next time what I'm going to talk about is what is called dynamic classification, which is, I think, an interesting idea with many applications. So I'll do that. It's a generalization of recursive sums, and I'll talk about that, I think. So that will happen, and I'll be at the study period later today. Okay, good. Thanks for your attention.